something that I think you guys will be interested in, or at least I hope that many of you will be interested in this. Because if not, then maybe we need to go find you a new, at least those of you that aren't Pearson, a new master's degree program or something. Although Callie may be like, I don't care about this. I want to get people to exercise. So we're going to talk about many of the physiological determinants of actual exercise performance, okay? And how we can take the things that we've learned about how muscles work and how the cardiovascular system works, and a little bit about the pulmonary system and the adaptations that occur with training and all of these things. And we're going to try to put all of this together and figure out what of the things that we've talked about so far are going to be the thing that is going to predict who wins a particular race, okay? And so I'm going to lead into all of this, that really we have a lot of data, or I say a lot, but we have some data that I'm going to show you guys. What we're going to focus on, this is much more about endurance exercise performance, okay, than it is anything else, right? I mean, if you really care about kind of like strength training performance, the idea is generate as much force as you possibly can, lift as much weight kind of one time as you possibly can. We have, in some ways, covered a lot more of those things. That's still an integrative process, but it's really much more about muscle and recruitment. It's not about kind of the interaction of a whole bunch of other different systems kind of imposed on top of all of that. And so, you know, this is going to be, I think in some ways there's stuff that's applicable to things like soccer and basketball or football a little bit in the midst of all of this, but just kind of remember that, you know, this is what we can much more easily test and control. Okay. All right. So let me do share screen. Megan, what are we drinking?
A protein shake.
A protein shake. Okay.
I haven't eaten enough protein today, so.
Okay. I was listening to a podcast about protein intake this weekend, and the effects of protein intake on skeletal muscle degradation following exercise. And I was pretty happy that they were talking about some of the studies that I actually showed you guys in the resistance training thing. So I was pleased. I was like, ooh, I picked the right ones. So there we go.
What podcast is that?
The podcast is called, hold on.
I'm kind of interested now.
Let me look. It's a good question, Alex. I think it is called hold on. No, don't play it. I want to know what the hell it's called. It's called We Do Science, from the Institute of Performance Nutrition, with Dr. Laurent Banach. But it's called the We Do Science podcast. It used to be like the We Do Science, like Guru Nutrition or something. Laurent started doing it. I've listened to it for many years. He was doing it while he was a PhD student. He's an older individual. I mean, older. He may be my age, but just recently finished. But he has a bunch of things. There's like 150 episodes, and they have people on to talk about everything. So it's pretty cool. Anyway, I have thought about making you guys like listen to the podcast and like take notes on things, because some of these people would do a better job of teaching stuff than I can. Okay, sorry. So what you guys see here, every time you complain about SPSS and every time you complain about Excel, I want you to remember that life could be worse. These are data from one of the first exercise physiologists to ever win the Nobel Prize. His name is A.V. Hill. These were published in 1925, okay? And weirdly enough, in 1925, you could publish data in multiple journals simultaneously. So this was published in The Lancet, but also in Nature and I think something else all at the same time, which is kind of a crazy thing. But the point of all of this is what you see in front of you. This is a logarithmic scale that has been imposed on basically graph paper, okay? And so this is a mostly hand-drawn figure. So whenever you complain about SPSS and having to make graphs, or you complain about Excel and having to make graphs, just know that we could be like, fine, here's some graph paper, do it all yourself, okay? But what you can see here is this is on the x-axis, this is the time that it takes to complete a particular race, okay? And so this is in seconds, and so it's from something that takes like 10 seconds out to 10,000 seconds and on and on. This would be 100,000 seconds out here. And then what you have is the average speed calculated in yards per second. Screw the metric system, damn it, we're Americans. In 1925, we're using yards in the midst of all of this. And so what you can see though is, look, here you have men who are doing like skating, ice skating. You have men that are bicycling, you have men that are running, you have men that were walking, you have women that were running. You will also note that they only got up to like 1,000 meters. They only got up to half a mile. Again, ladies, we were worried your uterus was going to fall out in the midst of all of this, much less we didn't really care about testing you guys in exercise because, I don't know, patriarchy. But look at all of these things, okay? And what I want you to appreciate from this is just the general shape of these curves, all right? And so what you are showing is that basically, as the time it takes to complete a particular event, which most of the time is going to correspond to covering a larger distance, okay? The time that it takes to complete, the longer it takes to complete an event, in general, the slower that the average speed in yards per second is going to be. And it looks like if you squint really, really hard and you kind of back out on some of these things, that maybe the kind of slopes of decline of all of these things are kind of reasonably similar in their shape, which might suggest that there is some kind of conserved physiology that is kind of limiting all of this particular performance, okay? And so in 1925, we didn't know what a whole lot of those things are. Now you guys maybe, you know, I could say like, hey, what are the things that are causing fatigue at 100 yards? Like, why can I run faster for 100 yards than I can to run 1,000 meters or something? And you guys are going to start talking about, oh, well, you know, aerobic metabolism, and this is anaerobic. We've run out of creatine phosphate, and we're accumulating lactic acid, so we got to slow down. Like, you guys know a little bit more about some of these things, okay? At the time, we didn't really know that. Okay, so from the same paper, here is a different, we've taken the logarithmic scale out on some of these things. We're looking at things like women who are swimming, men that were rowing, women's rowing, men's swimming, and you can look at the time, and this is so 100 seconds, 200 seconds, and again, we have average speed in yards per second. And what I want you to look at now is not whether or not each of these things is relatively similar in its speed, but look at the shape of these curves, okay? Notice how there's this exponential decay in performance time that reaches someplace out here, and 600 seconds versus 1,400 seconds, right? Basically the same pace. Here we have swimming, 800 seconds versus 1,600 seconds. We've basically doubled the amount of time we're covering, and things are going at roughly the same pace, okay? Now, I know everybody but Pearson probably wants to throw things if I mention math, okay? But we talk about this when you look at an exponential decay. When you model all of this out, you would say that this is decaying to something that we call an asymptote, okay? Where basically the slope of this line is going to become 0. And so at the asymptote out here, where it becomes horizontal, really it looks like it doesn't matter how much farther we make it, our pace is basically the same. And so what I'm going to tell you guys is that this was a thing that was observed in 1925. We could ask Jacob if he ever had a class with David Poole at Kansas State. Dr. Poole would want me to mention that he was one of the co-authors of one of your papers, that this particular relationship of sort of speed, if you will, or work rate and its relationship with duration, this relationship is conserved in birds, in horses, in dogs, in rats, in basically every animal that we can test. Also, if you look back in some things that are published, the walking pace while carrying a sword and a bunch of other things, he likes to tell the story of the Roman legions, that if you were a soldier in the Roman legion, if you couldn't march at the pace that they required, they would kill you. Like, that was the thing. Like, they would just conquer your plane, and then you'd get to be a soldier. And if you were a soldier, then they, you get food and you get taken care of and all of those things. But if you couldn't walk at whatever pace they wanted, then they would just kill you. Well, their walking pace of the Roman legion fits into a thing that if you were to look at sort of men's walking or women's walking now, it fits at about where we can figure out where this asymptote is now. Okay, so this phenomena has been observed and somewhat understood for hundreds or thousands of years. We just didn't know what to call it. Okay, and we're going to come back and talk about what this is. We're going to talk about the physiology in some ways that determines why this thing looks the way that it does. But then we're also going to talk about, if all of you go run, if all of you get on a bike, okay, and you're going to go ride a bike, or you're going to do the elliptical, or whatever it is that you're doing, you're going to go swimming, all of you have a relationship that we would call a power or a work duration relationship that looks like this for every modality of exercise, okay? And what I'm going to tell you is that for an endurance event, whichever of you can have your asymptote out here occur at the highest work rate, be that running speed or power output on the bike or swimming speed or whatever it is, you are going to win the race, okay? That's under most circumstances, you're going to be the person that's going to win the race, okay? So this concept out here is called critical power, okay? And it's called power because we measure power on the bike. It's easy for us to do these tests on the bike, but there is a critical velocity, there is a critical torque if we were just having you do like knee extension or elbow exercise and just do repeated maximal force things. And what I'm going to tell you all and what you're going to learn about all of this is that if we make your work rate above this asymptote on this power duration relationship, if your work rate is above, even ever so slightly, right, we can put you at like 4 or 5 watts above your critical power on the bike and leave it at that work rate, and you will fatigue and you will go to VO2 max. If I keep you kind of right under your critical power, if I give you food and water, you can basically cycle forever, okay? And so we're going to talk about, well, what is it about your unique physiology that contributes to determine what your critical power is or what your critical velocity is or something, okay? And sort of where lactate threshold fits in this, where VO2 max fits in this, where movement economy fits in this, where strength fits in this, where fiber type fits in this, et cetera, et cetera, et cetera. Okay? You guys with me so far? Okay? But it's really cool to me, and this was not something that I was ever taught. I learned about this particular concept when I took the job here, okay? I'd never heard of this before. I took the job here, and one of my now friends took the job at the same time as me, but he learned under David Poole at K-State, and they talked about this, and it blew my freaking mind. And I think it's really, really cool. It has a lot of really, really powerful implications because we can train this. We know that we can train it. And so maybe we need to think about, for doing endurance activities, how we would train differently to modify these things. Okay. So we're gonna talk about this idea of things now kind of historically that people have thought have contributed to exercise performance. Like, what is it that's gonna make a person a better endurance athlete, okay? And so what you see here, this is a figure. I believe this is from Mike Joyner and Ed Coyle. Mike Joyner, I think we've talked about, does blood flow and things, but he's at the Mayo Clinic. There was a really, really, really interesting article. It's about 70 pages long, so I didn't give it to you guys, but it came out in the Journal of Physiology like a month ago, talking kind of about the 2-hour marathon and those things, and that Mike Joyner kind of predicted it from using all of these things when he was a grad student. But before they really called it kind of critical power or critical velocity, they were calling it performance velocity or performance power. And all that this denotes is there is some speed or work rate that you can maintain during a 5K or a 10K or a marathon, right? There's some pace that you can go at, that you can, for the most part, you can maintain that pace kind of for the rest of the race, okay? And in theory, the person that can go at the higher pace without fatiguing is most likely going to do the best in that particular race. So they were breaking it down then into what are the things, right, that might contribute to this. And so they're talking about something that they were calling performance VO2. And so this was the aerobic metabolic component to all of this, that there is a, if you're running at some velocity or you're cycling at some power output, there's going to be a corresponding oxygen consumption. There's a corresponding aerobic metabolic rate that will occur at this velocity or at this power. And so the things that will contribute to that are going to be your lactate threshold, your VO2 max, and these things are going to probably have components of things like capillary density, stroke volume, max heart rate, hemoglobin content, right? Or hematocrit percentage. Mitochondrial function, so aerobic enzyme activity, and then there's going to be a little bit of these things where they're going to call distribution of power output, which may in some ways kind of be how much of your power output is coming from aerobic ATP production, how much coming from anaerobic ATP production. We know that there's going to be some amount of anaerobic that you're going to get all the time in this based upon your buffering capacity, that we're going to get a little bit of anaerobic and some aerobic, and we're going to reach some sort of kind of metabolic steady state from all of this that allows us to maintain these things. And so you have this, and then we have gross mechanical efficiency, which is going to be somewhat determined by fiber type, and then anthropometry and elasticity. So your individual kind of anatomy and biomechanics, kind of your limb efficiency and running form or cycling form, those kinds of things. So not a simple thing that leads into all of this. But we're going to kind of take a few of these things one by one and talk a little bit about kind of what's contributing in all of these things. Okay. So let's start back a ways. Okay. So one of the initial questions that people ask after some of the stuff from A.V. Hill was, do we think VO2 max contributes to aerobic exercise performance, right? Like, it would make lots of sense if this is a longer duration event. We think that aerobic metabolism is going to be our primary source of energy. It would seem likely that if you have a bigger VO2 max, then that would be helpful. So what I'm showing you guys here, these are some data from David Kostel's lab at Ball State that were published in 1976. But here you can have, and they actually listed their names, but these are the U.S. Olympic distance runners. And you've got their age, their height, their weight, but you also have here, we have their VO2 max, okay? And then you've got their best performance time and things out here at 400 meters, at a mile, 3 miles, 6 miles, marathon times. And what you can look at from all of this is, look, they have a VO2 max on average of about 77 mLs per kg per minute. They had good kind of collegiate middle distance runners. They were at about 70. Untrained men were at about 38. And you look at all of this and you think, well, these guys beat all of these guys in these races. Their VO2 max is higher. seems reasonable that maybe their VO2 max is one of the kind of primary things. The problem that we get from all this, and I think we've talked about this before, is what I want you to look at here is, so the person with the best marathon time is Frank Shorter. His VO2 max was a paltry 71.3. Okay, 71.3. Now I want you to look at this fellow, Indu, who had a VO2 max of almost 81, but he ran a marathon 12 minutes slower than Frank Shorter. So our guy with the lowest or the smallest VO2 max and our guy with our second highest VO2 max, the guy here kicks his ass at the marathon. Okay? And so, yes, these guys are better than here, but within this particular group, maybe there's something else that's kind of going on. So what might that be? Like maybe VO2 max is important, but maybe it's once you get to some kind of critical level of VO2 max, it becomes less important. Okay. Okay. So if we look at these things, all right, if we look at this, so, and I apologize, I should have the citation on here for this kind of thing, but we have 1 mile running performance, 2 mile running performance, and 6 mile running performance in these groups of athletes here. And so you've got a range of VO2 max from about 50 out to about 73 or 74. And if you look at this, right, there is a R of minus 0.84, 0.87, 0.88. There seems to be this kind of negative linear relationship between VO2 max and everything else. And indeed, when we look at all of this, right, we look at the interclass correlation coefficients, and we look at the kind of correlation of VO2 max to each of our other variables that are going to be out here. What we tend to see is that, right, in the midst of all of this, that VO2 is a better predictor in this than slow twitch fiber type composition, than activity of mitochondrial enzymes and things. So VO2 max is better than that. But I also want you to note that because you just had stats, okay, everybody take one of your hands and put it up on the screen, and I want you to cover up basically everybody that is under 65, like that has a VO2 under 65. So you've only got like 5 or 6 points on those, and really look at it down there at the 6 mile time, okay? And if I told you that those were the only data points that you had, maybe that thing starts to look a little bit less linear. It starts to look a little bit more like maybe there's not necessarily something that's going on, because like here, look, you got these guys who were like really fast in their 1 mile time, but they didn't have the biggest VO2, and there's some things. If you start throwing these people on this kind of low end out, then we get a little bit of a different story, okay? And so I'm going to tell you guys that what we kind of think now is that VO2 max matters. It very much matters, but it's not the whole ballgame, right? If you're going to compare a person who's a pretty reasonable college-aged, recreationally trained person who's got a VO2 in the 50 or in the mid-50s, right? That matters versus somebody who's in the 70s, right? But if you just look at people that are in the 70s amongst each other, it matters much, much less. And so you need some amount of big VO2 to kind of be in the ball game, right? But in people that are kind of within 10% or so of each other on their VO2 max, it matters much, much less. Okay, does that make sense, everybody? Y'all with me on that? Yes, no, maybe. I'm waiting for Keldon to get smacked in the head with a basketball, like a stray pass or something that comes sort of flying in there. Okay. All right. So I think that I gave you guys the article where it talked about what are some of the limiting factors in oxygen consumption, limiting things that are determining VO2. And so Alex, Jacob, you guys want to take convective and diffusive for us this time, or are you still a no on all of this?
I mean, we really talked about it for, like, he gave us a chapter, and we talked about for one section of that whole chapter.
Okay.
If the isn't convective, where it goes from the lungs to the tissue, and then diffusives, how the oxygen gets into the cells themselves in the tissue from the blood.
Yes, that is basically that's basically it. And so what I'm gonna show you guys now are a little bit of data on, right? So all of us have a VO2 max of some amount, okay? And the question is, well, why is that what our VO2 max is? Why is Callie's VO2 max? I don't know. In some ways, this is better to ask you guys after you've all had it tested in exercise phys lab, which maybe will get to happen next semester or not. I don't really know. Right? But like, why is Callie's VO2 max 50? Okay, and not 55, right? Is it limited by some kind of pulmonary diffusing capacity? So is there a limit on the amount of kind of diffusion of oxygen that we can get from the air across the lungs into the blood? Is it limited by cardiac output, right? Which would be this convective idea that, you know, is it how much I can actually get out, right, to the skeletal muscle? Is it limited by the amount of red blood cells, basically the amount of oxygen I can put in whatever cardiac output I have? That would be something that would be called convective, right? I'm moving it around, kind of a delivery issue. Or is it basically, am I limited by the ability of my skeletal muscle to use the oxygen that is being brought in at the lungs and brought and carried in the blood and delivered out here to my muscles, which again could be considered a diffusive issue. Like, how much can I get from the capillaries into my mitochondria and actually use, okay? And so the real answer to all of this, of course, like everything else, as some of you guys like to jokingly and sarcastically put on your tests, you know who you are. The answer is it depends, right? So, which I appreciate you guys. I appreciate you guys doing that, and putting it depends here. So let's look at a little bit of things, okay? So, is there a pulmonary limitation to these things? So here we have people breathing normoxic gas in this here and here. And then here we have people breathing hyperoxic gas. So we're giving them, you're breathing gas that's 26% O2, okay? And then we're having them do a VO2 max test under both conditions, and we're gonna look and we're gonna see does increasing the amount of oxygen in the air, which would maybe increase our ability to kind of drive oxygen into the bloodstream at the lungs, is that going to improve our VO2 max? And what you see is that in these normal people, basically no difference. In our highly trained individuals, yes, maybe it is helpful to some extent. And so again, we could probably ask Jacob, since he's the only one of us maybe that's had a class in actual pulmonary physiology, to kind of explain what is happening here. But there does seem to be a little bit of evidence that in very, very highly trained individuals, maybe even more so in highly trained women, more so than men, that there's some anatomical limitations to kind of bronchodilation and kind of the way the lungs are set up. Maybe there's a little bit of a pulmonary limitation in very highly trained individuals, okay? Because if we give them hyperoxic gas, then we can make their SaO2 go up. We can make their O2 sac go up, or at least prevent some of the decline in higher things. Okay, so maybe there's a little bit of this, but there's not a huge amount. Okay, I think I've already shown you guys. These are some data from Lauren Rowell that are very famous from the 1960s, and it's showing here is oxygen uptake, or max oxygen uptake, and cardiac output. Right. There's this nice linear relationship between maximal cardiac output and those kinds of things. And then here we have the response basically when we're doing training, right? We have people that are doing better as, we have a sedentary person, and then we have people that have been training for all of this. And you look at this kind of maximal oxygen uptake, and you can see these differences that as we make their cardiac output go up, this big thing here, by making cardiac output and stroke volume go up, right, we're gonna get this increase this increase in VO2. We may get a little bit of increase in VO2, obviously from an increase in AVH difference, which we'll talk about in just a minute, okay? So there's certainly some evidence that if you can make your cardiac output go up, if we can make the ability to circulate more blood that has the oxygen in it, okay, out to the muscles, then we may in fact be able to make your VO2 max go up, okay? Similarly, like if I gave all of you a blood transfusion right now, if you had given us, say, a pint of your blood, I don't know, like 3 months ago, and we infused it back into you right now, it would immediately make your cardiac output go up. It would immediately make your O2 carrying capacity go up, which would make your AVH difference go up. So it would immediately make your VO2 max go up. Okay, so we know on some levels, right, that there is some component of all of this that is important. Okay, so here we're looking at people doing just what I suggested, doing a blood infusion. Okay, and we're looking at changes in VO2 max, the total amount of hemoglobin in their blood. So this is basically how much blood do you have, but what it really is this is your hemoglobin percentage. So it's basically as we make hematocrit percentage go up, as we give you more red blood cells per blood volume, it makes your hemoglobin concentration go up, and that should certainly both increase the total amount of oxygen that you can carry in the blood, and it should make the kind of carrying capacity, the percentage that you can carry, go up. And so what we notice when we do all of this, if we give you a blood infusion, this is mostly just red cells, okay? As those things go up, then it can make your VO2 max go up, all right? So interesting things that are going on there. So it's a little bit of these things that are going to contribute to all of that as well. I find these data to be really, really fascinating as well. And these are data that have been taken from multiple studies and put together. And what you can see is these are people that have a certain maximal oxygen uptake, and it's the capillary to fiber ratio. If you guys remember, we talked about angiogenesis and atherogenesis, right? So not only do we can make the existing arteries that we have get bigger, so our pipes get bigger. We also increase the number of capillaries that we have per fiber with aerobic training. And so look at this, as VO2 max goes up, the amount of capillaries per fiber is also going up. So you can imagine that if I train and I make cardiac output go up, I make blood volume go up, okay, and I have more capillaries, now I can circulate more blood. I can therefore have more red blood cells in that blood because I have more blood. So there's actually more O2 in there. I have more capillaries, so more of that can get sent off to the muscle fibers. And so that should, in theory, then maybe give myself a chance to have more diffusion of the oxygen out of the capillaries into the fibers. Okay, but all of that is going to be dependent upon what? This other end of the diffusive thing, which is mitochondria. Okay, it's going to be mitochondria. And so what I'm showing you guys here is you can see their kind of fiber type percentages, which I think is really interesting. Our elite guys were about 80% slow twitch. Our middle distance guys were about 62%. And then our untrained were at about 58%. Now, I would tell you all that middle distance runners here, good collegiate distance runners, are going to look much more fiber type percentage wise like good Olympic ones. That because these guys were more middle distance, they don't need the slow twitch ones quite as much. Anyway, but what you can see then is if we look at, and I apologize, at the end of all of this, is I want you to look at SDH, okay? SDH percentages, there's not really any differences in LDH or phosphorylase enzyme activity between all of our groups, okay? But there is this very, very dramatic, and this is actually concentration, or it's micromoles of oxygen that they can kind of drive per gram of muscle weight per minute. But there's this much higher rate of this, likely from having many more mitochondria in the kind of elite folks. So if I have more mitochondria, I can keep the O2 partial pressure inside my cells, the muscle cells, lower, which makes that diffusion gradient from all those new capillaries that I have, it keeps it big, which is going to draw lots of oxygen in. Okay. So I think all of this is kind of an interesting thing. So if you ask me the question, all right, well, which of these things is the absolute limiter for everything? The answer certainly is it depends. And they all matter. They're all going to work in concert in a lot of these things. Okay. So there's been a lot of things, and it depends upon who you read and what you want to read in those articles. People feel very, very strongly. I do not feel that strongly about all of this, but other people do. And so I feel like that I need to kind of make these points to you guys that does it really matter if your max VO2 is limited by here, pulmonary? Is it limited by basically central circulation? So is it limited by cardiac output, right? Or is it limited by the ability of the muscle to actually do something with all of that oxygen? And it really drove a lot of stuff in our field for, many, many, many years, 20, 30 years, okay? And so what I'm going to try to show you guys is the change in VO2 max, basically pre to post training. This is a percentage change, okay? And we've got an endurance trained group, we have a no training group, and then we've got this same kind of group where we're having them doing exercise with both legs. So this is a group that was doing exercise with just one leg, okay? And then we then had them, you're going to see that in the one leg, your VO2 max during single legged exercise, during like single leg cycling, went up about 25%, okay? But then when we had these same people exercise and ride the bike using both of their legs, it only went up about 10%. We only trained one leg, okay? And so this is going to become a really, really important kind of thing. And it's telling us, one, that the adaptations are very specific to a particular kind of muscle and muscle group. But it's also going to tell us something about if we can make sure that we have enough blood flow. We can kind of overshoot cardiac output to one particular limb versus whole body exercise. We're going to get different answers, okay? And so here you can see cardiac output and then how much of the kind of measured muscle blood flow is going. And so if you look at the knee extensors when you're doing one leg knee extension cycling, right, you're only going to max out your cardiac output at about right here. So we do two-legged exercise. We know that we have more cardiac output, that we can get more, sending all of it to the one leg. Versus during two-leg cycling, this is measured in the same leg as here. That leg is not getting nearly as much blood flow because it also has to go to the contralateral leg and everything else. And so what you can see basically is that if we set up a situation like this, we can ensure that a huge amount of blood flow can go to this one leg. And we can try to create a situation where we're certain that cardiac output is not going to be limiting in this instance. And is that then going to kind of, if we do training and stuff, can we show the effects of just changes on the muscle end? Whereas during two-legged exercise, it's a little bit more difficult because we have to have competition for all of these things, okay? All right, so I want to see what time it is. It is 3:45. So we spent a lot of time early on with people talking about VO2 max and its determinants of performance. And then we think VO2 plays some role, so then what are all the things that are going to determine what your VO2 max is? What's the limiting factor in VO2, right? Is it how many mitochondria you have? Is it how many capillaries you have? Is it, how much kind of cardiac hypertrophy we see or expansion of blood volume? All of those things that we've already talked about that happen with training. And in some ways, the answer is yes, it's all of them, okay? Or it's some combination of all of them. Because I can send you to altitude and make the pulmonary side of things limiting, right? Or you can do one-legged exercise or arm-only exercise or something where you're not going to reach your maximal cardiac output, and I can make it where it's certainly going to be a muscle issue, where it's how much oxygen can the muscle itself actually use, because we're never going to have a problem with mismatching cardiac output to what the muscle needs. So it's going to be a little bit dependent upon kind of the event. But most events are running or biking or swimming that are relatively whole body events. So we need to understand, are there some other parameters of things that are going on that are going to interact with how much cardiac output gets to the muscles and how much oxygen they can use. So what I'm going to show you guys here, these are data from David Kostel's lab, and these are things that they put together from multiple different studies. And what you can see is this is basically they're doing lactic acid as a percentage, but it's kind of the same people that they tested across different competitive race things over several years, and they just picked out that at this very short distance, this was some maximal amount, and they express it relative to that. And so if you look at these things, let's have a look at this. This looks a whole lot like as distance increases or as time increases, then as it goes out, my lactic acid kind of levels at or during that race are going to fall, okay? The shape of this looks a whole lot like the shape of the critical power curve, doesn't it, right? And so now we're beginning to kind of match up some additional physiology on top of things. So what this is telling us is when you're doing very, very short races, right, maybe VO2 max matters, but it doesn't matter as much because you're going to max out your anaerobic metabolism as well. And when we get way out here, it's almost wholly aerobic exercise kind of metabolism that's going on. And so maybe in that instance, your VO2 max or where your lactate threshold occurs relative to your VO2 max is going to be much more important for determining this thing out here. And I want you guys to look at this idea here that at these last two distances, right, their amount that covering that distance going as fast as they can, they have relatively similar lactate levels. And that's going to again become very, very important. But they are up a little bit over rest. Okay, so when I was taught back in the pseudo dark ages, okay, back in the age of regular light bulbs and not these LED light bulbs that we all have now, we'll say that, okay, I was taught that, and there's data, and I'll show you guys some of that data, that this here, okay, whoever had a lactate threshold that occurred basically at the highest percentage of their VO2 max, or whoever could run the fastest at this place out here, at this place where they were making basically slightly over resting lactate levels, those were the people, that was the thing that would determine who would win an endurance race. And as I now know, that's not a completely wrong answer, but it's not the whole answer, okay? It's not the whole answer. So let me show you guys a couple of other things. So now we're talking about, you guys remember lactate threshold, right? You remember that at a certain place, at a certain percentage of your VO2 max, so at some running speed, at some cycling power output, at some walking up a particular grade or something like that, we're going to tip over, right? And we're not going to be able to match the production of lactate to our ability to clear lactate out of the blood. You guys remember that, right? Way back in the day, some sorts of nods of heads, yes, maybe, no, yes, okay. So that place where our production is going to begin to exceed our clearance, that is lactate threshold, okay? That's lactate threshold. And so that's going to occur. And we know that once we start making lactate, we're really making lactic acid, it's going to dissociate and we're going to begin to accumulate metabolic byproducts that are going to lead to fatigue, okay? So what you guys can see here is this is the time to fatigue during exercise at 88% of a person's VO2 max. And each number on here, okay, represents an individual participant. And people that have high capillary densities were denoted basically by the folks with the arrows. And so even though 4 is not on the arrow, what they're looking at basically is look at 8 and 7 and 2 and 1 and how these people have sort of one kind of a slope of this, and the folks that had lower capillary densities didn't. You have less capillary density, shorter time to fatigue, less capillary density, you're at a lower percentage of your VO2 max at lactate threshold. And so these people are way up here. Their lactate threshold is pretty close to their VO2 max. So that means aerobically, I can run at a pace that's going to elicit a high percentage of my max without accumulating appreciable amounts of lactate, which means I can avoid fatigue while being at these relatively high kind of VO2 levels. Okay. So we talked about maybe capillary density matters for lactate threshold because I need to be able to deliver more oxygen, but also that's going to help me from a clearance standpoint. I've got more places to diffuse it out and get it off to someplace else. Okay. So what I'm going to show you guys here, we've got some data here at the top, and then the graph at the bottom is from a study that one of my former master's students did in my very first job. This is one of our papers. So what you can see here is running velocity measured at lactate threshold and performance. Okay, and so this is performance during a 3-kilometer test. All right, you're going to run 3 kilometers. You're going to run, I don't know, what is 3 kilometers is a little over, it's like 1.75 miles or something like that. Okay. And so what you can see then is that, right, VO2 max has a correlation coefficient of about 0.7. So having a higher VO2 max helps, you're going to perform better. Your VO2 at lactate threshold is a better predictor, right? And then your VO2 at whatever you're going to reach, the VO2 at the work rate that elicits 4 millimoles of lactic acid is not going to be quite as good. But then we look at the running velocity at lactate threshold, and the running velocity at 4 millimole are the single best things that correlate in the midst of all of this, okay? And so then what we did as a follow-on to all of this, the idea behind this is that whoever can run the fastest at their lactate threshold is going to be the best endurance performer, okay? And so there are going to be a couple of things that will contribute to all of that, but that's the supposition. And so I would say that this is the thing kind of in some instances that was more popular in the 90s and the early 2000s, as this is the stuff that predicts performance, right? We need to talk about lactate threshold. So we took, these are, and we statistically cheated a little bit with this, but we took men on the cross-country team and the women on the cross-country team, and we looked at their running velocity at, my student wanted to call it the anaerobic threshold. It is lactate threshold. We can all wring our hands about what lactate threshold is versus anaerobic threshold versus second lactate threshold. Any of you guys that had Dr. Mike for undergraduate exercise phys probably learned all of those things. There's not really a huge, there was at one point from Carl Wasserman, who's a very, very famous exercise physiologist, there was some thought that they were kind of different and distinct things. And we now know that they're all kind of the same things. There's less fuss over what's what. But this is how fast can you run at lactate threshold. You guys will sort of do a thing, right, Megan? Where you all determine your power output at lactate threshold in exercise phys lab, but you did it during a graded maximal exercise test. Is that right?
Yeah.
Okay, so we did this where they ran on the treadmill at a certain velocity. So like we did a VO2 max test on the treadmill. We figured out what their running velocity needed to be at their ventilatory break point, which we talked about, before we tested you guys on. And so then we went kind of a little bit under all of that. And we had them run for 3 minutes at a velocity and then stop, and we would measure their lactate. And then we would bump up basically their running pace, ever so slightly, like a 1/4 mile per hour, and have them run again. And then they'd go 3 minutes, and we would stop, and we would measure them. So we were trying to be very precise at catching where they go from their resting levels to now it's starting to elevate, okay? Which you need to be more precise. The way that you guys will do it in Dr. Deb's lab, you kind of gather it while people are doing their VO2 max test, and you can get that data by doing all of that, but this is a little more precise. And then we graphed all of this against their NCAA cross-country meet pace, okay? And so the women didn't run as far as the men. The women ran a 5K and the men ran an 8K, I believe. But we took it as pace. So they're miles per minute or meters per minute. And you look at all of this and you run the correlation here, and we got an R-squared value of 0.95 between their running velocity at lactate threshold and their actual NCAA pace on these kinds of things. So it kind of lends some additional credence to how fast you can run or what your power output is at lactate threshold is likely going to be predictive of sort of your ability to go at a certain speed or at a certain power output during kind of endurance exercise. Okay. So getting into this idea of performance VO2 that Coyle and Joyner talked about, right? They were saying you have some certain VO2 max, you have a percentage of that VO2 max at which lactate threshold occurs, and they were kind of defining initially performance VO2 is basically your oxygen consumption or your metabolic work rate at lactate threshold, okay? And so we figure out what this work rate is, or what the energy you can produce at lactate threshold is. We then figure in your running or your movement economy. So it takes Kelvin X amount of ATP to run at a particular pace. It takes Cali less or more to run at that particular pace. And so their economy basically is metabolic cost per pace. You figure out I've got a certain amount of metabolism, I have a certain running economy. These two things together are going to determine how fast I can go at that metabolic rate. And that is going to, these things together are going to be really, really helpful for us predicting your distance performance. And indeed they are, okay? They are. But there's a couple of other things that are going to kind of play into the midst of all of this. Okay, so if you really care about movement economy, which some people do, I just want you to look at this giant thing that is right here. And I can tell you that there's a huge, huge, huge number of things that contribute to movement economy. Many of them are so far beyond my ability to understand things. But there are things like your physiology, but then the environment, right? Your training status, the biomechanics of how you move, right? But then also your limb morphology, your individual like muscle and tendon stiffness, your body weight, your body composition. All of these things are going to work in concert to kind of help us in the midst of all of this. If you want to think about this in some ways, think about how you can make your movement economy bad. I'm going to run while waving my hands over my head like this, okay? Rather than run with my arms down like all of this, okay? If I'm running like this, I'm using more energy of my kind of, I have a certain metabolic capacity before I make stuff that causes me to fatigue, and I'm wasting some of that energy in my arms waving over my head, okay? And so, but I want to have good running form, but also it's helpful if I have a certain limb morphology and these kinds of things. This is in a lot of ways, if you just look at kind of qualitatively, if you look at distance runners, a lot of them aren't super duper tall, but for their height, they have long legs. They're very built like my wife. They're kind of high-waisted, not a lot of midsection, so they can cover stride length per height is going to be pretty big in comparison to people like my daughter and I that are all midsection and have T-Rex arms and legs, okay? And so whereas people that are really, really good swimmers, if you want good swimming economy, it's helpful to have short legs, long torso, and long arms relative to your body weight because of the kind of mechanics of swimming. That's going to be really, really helpful, okay? And so some of this we can't really train. but flexibility, your ability to store elastic energy and your tendon stiffness and stuff, maybe we can train that a little bit. But then we also have some really interesting data on if you resistance train and you're a distance runner, it makes your running economy go up. And you want to make people mad, find a distance runner and tell them that they've got to start doing power cleans and they've got to start squatting, and they become unhappy very, very quickly. A lot of them because they've never done those kinds of things. But there's very, very good data that if you can increase your maximal strength, it will improve your movement economy. So in that way, distance runners need to do some resistance training. You maybe don't want them to be like giant people because you got more muscle, your VO2 can go up, but you also have to carry that muscle. So, okay. So here's some data. They're going to kind of look at O2 uptake in 2 international folks. Like here you can see subject number 1, basically at a particular speed is using their VO2 at that work rate is going to be lower. So they have more economical kinds of things. And then here we have 2 people that you can look at basically their VO2 max or the percentage of VO2 max and their kind of velocity things. We can graph all of these things out and you can project them out to where you think their max is and their kind of race pace or their velocity thing is going to go up. And so we do know that this matters, okay? Being as economical as possible, you only have a certain metabolic potential, and being as economical, using as much of that metabolic potential to propel you forward is going to be really, really important. Okay, so let's come back to this, and now let's talk about what we know about this particular relationship and how it applies to all of those things that I've already talked about. Okay, so here is something. This is what's called the power or velocity duration relationship. Okay, and so if you looked at the Poole and Andy Jones and David Poole and Annie Van Hattalo, which we could have an entire day talking about kind of that group of people and their things, but it is a relationship that looks like this basically. Okay, and so this line right here, this is this kind of exponential decay in power or velocity that we see as we increase time. This is the relationship that we see that looks like this relationship, okay? And so here we've drawn in this asymptote, basically. And the asymptote of where this plateaus out here is going to be the work rate, the power or velocity that we call critical power or critical velocity, okay? And so what you can see is here's where critical velocity or critical power exists. In these same individuals that we test, their lactate threshold occurs at a power or velocity that is lower than their critical power or their critical velocity, okay? And so if we imagine that VO2 max is somewhere up here at the top, and then there's this relationship or this threshold here, and then there's also the lactate threshold that is going to be there. This is also sometimes called, these are the transitions between different zones of exercise intensity. So you have any kind of exercise that is going to occur where you do not accumulate lactate above rest is considered moderate intensity activity. Anything that occurs between lactate threshold, so you're going to get lactate over threshold, but that is under or up to critical power, is termed heavy, the heavy intensity domain, which we very often might think of as vigorous intensity physical activity. And then anything that happens over critical velocity or critical power is this very, very high intensity that we often term this is the severe exercise intensity domain. And so you guys will see why some of this is important. And so the way that this relationship is derived in most people, the best way to do this is you do a VO2 max test on people, okay? Then you have them come back for 3 or 4 additional times. And what you do is you pick out a power output or running velocity that you think is going to elicit a certain percentage of their VO2 max. And you put them on the treadmill or the bike and you say, you're going to be at this power output, or you're going to run at this velocity, and you're going to run or bike until you can no longer go. Okay? You're going to go to what we call volitional exhaustion. And you do that on one day, and you give them a power output or velocity that's very close to VO2 max, and they don't go very long. And they come back after a couple of days of rest, and you give them one that is significantly lower than those things, but that we know is over T-vent, it's over ventilatory threshold, and they go for a much longer period of time, but yet they still reach volitional fatigue. And then you give them these things that are in between, and then you use this and you graph them out, and then you run the mathematical calculation, you do a curve fit on all of this, and you find the asymptote. And that should tell us roughly where their critical power or their critical velocity occurs. Okay. Now, there are ways to do this in a single test, but none of you want to do it. I promise you that. Okay. Any of you that have ever done a Wingate test? So imagine that what we're going to do is I'm going to make you essentially do a Wingate test where you're going all out for as long as you possibly can. And at some point, as you continue going at that work rate, you sort of fatigue down and you slow down enough to where it plateaus off and you can keep the thing going, but you've had to slow down so much that you basically slow down to your critical power. Or they will do a one-off test where you do a VO2 max test, and you cycle until you reach VO2 max, and then once you reach that, then you just keep going for like 3 more minutes. It's like, I've reached max, okay, and then we're going to let you adjust your power output, and you just kind of, you just keep going down basically until you again kind of bottom out. And this is the pace that you can keep up with. That's your critical power. I've seen videos of these things. I've not actually ever done one myself. We've never done it in the lab in that particular way. It looks awful. It would be hard to do that in people that are not very well motivated and are not very good athletes. Okay. So it is now recognized, okay, and this is in some ways one of the big points of the Jones and the review article that I gave you guys on all of this, that critical power represents an important parameter of aerobic metabolic function, okay? That in addition to lactate threshold and VO2 max, all of which are these critical parameters that are going to contribute and give us information about how well your aerobic metabolic systems work, right? All of which are going to represent this kind of balance of fiber type and mitochondria and cardiac output and blood volume and hematocrit percentage and lung function. Critical power is also, or critical velocity is also something, okay, that is going to, that we need to consider in the midst of all of this. And so things that are really, really interesting that I want you guys to understand about all of this, and then we'll probably call a stop for today, and then we can pick up some more stuff on Thursday, is here is a graph of oxygen consumption, okay? And this line here represents lactate threshold. This line here represents, these are work rates that would elicit VO2 max, right? If I give you the work rate that you reach at VO2 max and I have you go, here's the one that's going to exist at critical power, okay? And so what happens is, if I give you a work rate that is under lactate threshold, you basically come up and you plateau off and you reach a metabolic steady state. Your VO2 levels off and it stays right there, okay? If I give you a work rate that is just under critical power, it goes up and you're going to get a little bit of this slow component rise that we talked about earlier. So it kind of goes up and then it drifts a little bit, but it will eventually, not quite as quickly, but it will also eventually reach a steady state, okay? It's a slower climb and kind of this double exponential decline, but it will also reach a steady state. At any work rate that is as little as 2 or 5 watts above critical power, there will be no ability to reach a metabolic steady state. Your VO2 will just climbs up until you reach VO2 max, okay? So if your critical power is at 200 watts on the bike, I can give you 205 watts and tell you to ride at 205 watts. And if you keep going and I yell at you, you will end up doing a VO2 max test at that 205 watts. It may take 20 minutes, but you will end up going to your VO2 max. In the same way that if I gave you 300 watts, you would ride it and then you would reach VO2 max, okay? But right at critical power, you will reach a metabolic steady state, and that's important, okay? The fact that you can reach a oxygen consumption steady state, anything at or below critical power or critical velocity, you reach an O2 consumption steady state. Anything above, you will not, okay? So here it's showing the work rates at these kinds of things, and the critical power is between VO2 max and lactate threshold. But the other thing to also keep in mind is if you look at blood lactate levels, okay? And this is the part that I was never taught that I think is really cool, is any exercise under lactate threshold, you're not going to get an increase in lactate, right? Anything under critical power, you're going to get an increase over lactate threshold, but if you keep going and it's under critical power, you will reach a lactate steady state, okay? That's one of the other denotations of critical power or critical velocity, is you will reach something that sometimes is called maximal lactate steady state. So there is a work rate where, and your maximal lactate steady state might be at 4 millimoles, or it might be at 8 millimole, or it might be at 6 millimoles, okay? But if you are at or under critical power or critical velocity, you can reach a maximal lactate steady state. So you kind of get tipped over, right? Your production is exceeding your clearance, but you are going to have some capacity through buffering and other things to handle some level of increase in lactate. Everybody can. Some level of increase in lactate before it's going to be so much that it's going to cause you to inexorably fatigue and reach VO2 max. Okay? I was simply taught that once you got over lactate threshold, you were going to fatigue if you stayed there. And the more nuanced definition of that is, no, it's actually critical power, right, or critical velocity. That's the threshold. If you get over that at all, you're going to go to fatigue. Okay? So basically, and I have some data a little bit later on at the end of all of this to show you guys, what we now know, right, and we now think is that the person that wins an endurance race is the person that has the highest critical power or the highest critical velocity, right? And so VO2 max contributes to critical power. It contributes to critical velocity, but so do a bunch of some of these other parameters that are going to be in there as well, okay? And so you need a certain amount of VO, if you have a VO2 max of 70, your critical power occurs at 60% of your max, right? 70, that's going to be at 42, but I have a VO2 max of 40, and mine also occurs at 60%. Mine's at 24 mLs per kg per minute. So you have almost double, right? Almost double the oxygen consumption capacity at critical power than I do. So you can obviously run faster or do a higher power output than I can at all of that. Okay, so bumping up the top end of that is good, but in people that are similar on the top end, that have similar VO2 maxes, whoever's critical power, which is also partially determined by lactate threshold. So whoever has a lactate threshold and a critical power that is closer to their maximal VO2, right, is also going to be able to use a larger percentage of that VO2 without kind of fatigue. And I think I had mentioned to you guys that in our data, I pull this back, okay? So our best female distance runner here had the smallest VO2 max. The girls that were down here all had bigger VO2 maxes than this girl. Some of them by like 15 mLs per kg per minute. Okay. Our runner who was here, her VO2 max was, it was like 46 or something. Her lactate threshold was at 93% of that. So her lactate threshold was at like 42. So she could basically run at VO2 max for a race. are people down here who may have had a VO2 max of like 55 or 56. Their lactate threshold occurred at like 60% of their max. And so in theory, if we could train this person better, we could raise their lactate threshold, raise their critical power, their critical velocity in this instance, up much closer to their max. They have the potential to be a much better distance runner than our person here. This girl had essentially maxed out her physiology. She was as good a distance runner as she could possibly be, okay? Which made her a pretty good Division II kind of all conference level distance runner. But these girls maybe could have been much, much better. So anyway, all right, we'll stop there, guys. We'll stop there. So on Thursday, we'll do critical thinking. We'll talk a little bit about the articles and everything, and we'll kind of clean up the last little bit of all of these things. And we'll also talk about anaerobic work that you can do over critical power and something that's called W prime. Okay. All right. So if you guys care a whole lot about these things, I find this to be like one of the coolest and